Topic 11.1, EM induction. So from the data booklet, we have this equation. This is the equation for magnetic flux. Capital Phi equals BA cosine theta. Phi is the symbol for the magnetic flux. B is the symbol for the magnetic field strength. It's a vector. A is the surface area of your loop, and it has an orientation. So it's also a vector, and cosine of theta, that is the angle between your B field and the surface area, or the area inside of the coil. We have the induced EMF equation. This is Faraday's law of induction equation. Epsilon is the induced EMF, the induced voltage inside of a coil or inside of a wire with n number of turns, and through which you have a changing flux over time. The negative symbol, the negative sign, just means that whatever EMF is induced inside of the copper or inside of the current carrying wire, that EMF tries to oppose the changing magnetic flux. So the induced EMF causes an opposing magnetic field to whatever magnetic flux is penetrating the wire. We have the EMF induced in a length of wire. Epsilon is B, the magnetic field strength, times the velocity, times the length of the wire inside the magnetic field. And we have the EMF induced for n number of turns of coil, BVL, where L is the length of a side of the coil, times n number of turns. All right, electromotive force, EMF. Please note, it's not really a force, but I am going to talk about a real force on this slide. So we'll consider a magnetic field, a B field provided by a horseshoe magnet. In the horseshoe magnet, or any type of magnet, the electric field lines are represented out of the North Pole going into the South Pole. If we put a stationary charge, a non-moving charge within this field, so like a proton, the proton would not experience a magnetic force. It wouldn't accelerate in any direction. Note that it doesn't have, protons don't create a magnetic field around them, rather they create an electric field around them. However, if we make a proton move within the B field, it will experience a force. This force I'm describing is not the electromagnetic force, or the electromotive force. EMF is a voltage. But the force in this example that the proton experiences is a magnetic force, and it can be calculated using this equation from topic 5. F is equal to Q times the velocity of the moving charge. Q is the charge, V is the velocity of the moving charge, V is the strength of the B field, and sine phi is the angle between your velocity and the magnetic field strength. All right, it should come as no surprise that a moving piece of wire or a conductor inside of a magnetic field produces a magnetic force on the charges in the moving wire. So if we took a rod and we had a strong enough magnetic field like the one represented in the diagram, you would get this movement of charges as the rod moves inside. And in case you forgot how to read the orientation of the B field, I can see that the B field is pointing out of the screen towards me because I see the arrowhead. So in this case, it's out of the screen. If the B field was going into the screen, remember this, I would see the tail of the arrow that's going in. And you can recall your right-hand rule. Your fingertips point in the direction of the B field, so the fingertips on your right hand point in the direction of the B field. Your thumb points in the direction of the moving charges. Thumb is moving charges. And the palm of your hand faces the direction of the force, the magnetic force on the moving charges. So if you do that for this example, you can see that the force acting on the moving charges should be opposite to the direction the charges move. And we'll go into greater detail with that in the upcoming slides. Practice number 1. A conducting square coil is placed in a uniform magnetic field. What is the correct direction of force that acts on a side of the coil? So let's use that right-hand rule. So we see we have 4 sides of this coil, side A, B, C, and D. Your thumb on your right hand points in the direction of current. That direction has been labeled for us, and for position A, I'll start with that side. It goes up, so I point my thumb up. My fingertips on my right hand now point into the page, which leaves my palm open to face the direction of the force acting on the wire. So my thumb points up along the wire, my fingertips point in, my palm points to the left, so that is the direction of force acting on this side. So let's do part B, or side B, because A I can eliminate. Same thing, I have my direction of current, so I point my thumb in that direction, my fingertips point into the board, the face of my palm points in the direction of the magnetic force, so that is up. So again, I can eliminate choice B. It's left for you now to analyze sides C and D, and you should get the right answer. Induced EMF. If the north pole of a magnet is suddenly thrust through a looped conductor, a current is created. This is what we'll see with our investigation coming up. So if I had a galvanometer or an ammeter, something that could read the current, galvanometer is better because it has negative direction. You can see that as a magnet is forced through a loop, it generates a current temporarily. So true or false? Current travels through the circuit only while the magnet is moving through the loop. And the answer for this is, of course, this is true. It's only moving charges that are affected by a magnetic field. In the same way, it's only a changing magnetic flux or a changing magnetic field that induces current. So true or false, the current direction depends on which direction the magnet is being moved through the loop. This is also true, very true. So the current direction acts to oppose whatever direction the magnetic field is traveling in. So this is something that we are going to have to document. We're going to have to be really careful with in the upcoming investigation. Since moving a conductor through a magnetic field produces a current, this very action must therefore induce an EMF, a voltage, in the conductor. Likewise, moving a magnetic field through a conductor produces a current. This action must therefore induce an EMF in the conductor. So all we need then is relative motion between some current carrying wire or some potential conductor and a magnetic field in order to induce a voltage. So this is the principle behind electricity generation using turbines and magnets. Coils of wire are moved inside of a very strong magnetic field, and this produces an EMF which can drive current. Let's consider an experiment where the plane of the loop is in the same plane as the moving magnetic field. So here's our apparatus, and I want you to imagine that this edge, this front edge of the loop, is actually coming directly out at you, out of the screen. The far edge of the loop is going into the screen. This axis is pointing out at you. So I know it's hard to visualize 3 dimensions on a two-dimensional plane, but just bear with me. So we're going to push this magnet, this bar magnet, towards the loop, not through the loop, but along the edge of the wire. And what you see is that, well, true or false, because of the orientation of the loop, most of the magnetic field lines do not pass through the area of the loop. This is true. The area of the loop is here, like sideways. And this area, it is oriented such that you have like a 90-degree angle with respect to that surface area. So these magnetic field lines are at a 90-degree angle with respect to this surface, with respect to the normal of the surface area. So true. Because of the orientation, most of the magnetic field lines are not passing through the area. So true or false, there is no current generated in this experiment. That is a definite true. There was no current generated. All right, because this orientation between the area of the loop and the B field is really important, this quantity called magnetic flux needs to be defined. Capital phi, the magnetic flux, equals B, the field strength, times A, the area of the loop, times cosine theta, where theta is the angle between the normal of that area and the B field. So as previously stated, this direction of the area needs, when we're talking about the area, we are talking about this vector that comes out. This vector that's oriented perpendicular to the plane of the area. So when the B field and this A vector are aligned, this area vector, you get maximum flux. However, when the B field and the area vector are oriented away from 0 degrees, then you have minimum flux. Practice problem number 2. 3 conducting loops, x, y, z, are moving with the same speed from a region of 0 magnetic field to a region of uniform non-zero magnetic field. So the region of 0 magnetic field is on the left-hand side, it's in gray, all this gray grid, they've gridded that off for you for a reason, to a region of uniform non-zero magnetic field strength, which is on the right-hand side represented by all of those dots. Which of the loops experiences the greatest magnetic flux the instant it enters the magnetic field? So let this equation for the magnetic flux be your guide. Capital phi, I don't know why I keep saying that. Capital phi equals B times A cosine theta. And you need to decide, does the B field strength change? Or is there some difference between the B field strengths from X, Y, and Z? Is there some difference in the area of X, Y, Z? Is there a difference in the angle for X, Y, Z when they enter the magnetic field? Is there a difference between the field direction and the direction of the normal to the plane of these areas? So you need to decide. And maybe they're all the same. Maybe there's one that has a greater magnetic flux the instant it enters this magnetic field. Okay, recall from topic 8.5 that although the intensity of radiation from the sun is 1380 watts per meter squared, when it reaches our orbit, it spreads out over progressively larger areas. So these yellow arrows represent the intensity of the sunlight. This sunlight reaches our planet, and you notice that as the angle changes or as the latitude changes, the amount of this sunlight reaching the surface area changes. So the solar radiation flux, capital phi equals IA cosine theta, is also a scalar quantity. I is a vector, that's the intensity of the radiation, and the area vector has a magnitude of 1 meter squared. Theta in this case would be the latitude. Magnetic flux is measured in Tesla meter squared, also known as a Weber. 1 Tesla meter squared is 1 Weber. And magnetic flux density is defined as the magnetic flux per unit area. Thus, let's do some derivation here. Magnetic flux density is capital phi divided by A cos theta. And from the definition of magnetic flux, we can see that the magnetic flux density is BA cosine theta. I've replaced capital phi with BA cos theta divided by A cosine theta, A, and the cosine thetas cancel. Thus, the magnetic flux density equals B. So, magnetic flux density is the same thing as the B fields. The magnetic field strength and the magnetic flux density, same thing, and they are both a vector. Hey, speaking of this difference, practice number 3, what are the units of magnetic flux and the magnetic field strength? So A, B, C, or D, hopefully you've been paying attention and taking notes and you'll get this question right, not only in the worksheet, but also in the Edpuzzle. Okay, if instead of a single loop we make a coil of n loops, the flux, capital phi, through each loop then gets linked to each of the other loops in what is termed flux linkage. So essentially this the magnetic flux gets increased with increasing number of loops. So we can drive the magnetic field through the loop. What you get is a greater induced EMF. These EMFs just add together, again, creating a larger total sum. Okay, so these demonstrations have shown that only while the flux is changing does voltage get induced inside of a coil. Here we can see again, only when the magnet is in motion will there be an induced EMF. Since flux, capital Phi, equals BA cos theta, there are three ways to change the flux, one of which is to change the B field strength. Number 2, you can change the area or the shape of the coil. Or number 3, you can change the relative orientation theta of A and B. Number 3 is the way a generator produces electricity at a power plant. A coil in a generator is rotated by a turbine, thus changing the angle. You change the orientation between your area, the direction of your area, and the B field. That induces EMF. Okay, here we are, the big equation in all of this, Faraday's law of induction and Lenz's law. Faraday's law states that the EMF induced in a coil is equal to the rate of change in the flux linkage in the coil. So we have the equation, epsilon equals negative N, delta phi over delta T. Lenz's law states that an induced current will have a direction such that it will oppose the change in flux that produced it. This is Lenz's contribution to the Faraday's law, that negative sign. So whatever goes on, whatever EMF is induced in the coils, it is induced to cause the coil to resist a change in the flux. Okay, number 4 is a little more abstract, but I think we can get it. The plane of a coil is positioned at right angles to a magnetic field of flux density B. The coil has N turns, each of area A. The coil is rotated through 180 degrees in time t. What is the magnitude of the induced EMF? So between 0 degrees and 180 degrees, we're going to figure out what's the total EMF, the total EMF produced by this rotating coil. Now, if this question has for the average EMF induced, it would be 0, because you would have current driven in one direction, then it would go to 0 at 90 degrees, and then current would be driven in the opposite direction when the coil was rotated to 180 degrees. So the average would be 0, but we could get the total, or the sum, the total magnitude of the magnetic field. Of the induced EMF when the coil is positioned at 0 degrees to the B field and at 180 degrees to the B field. And so this is what we'll do. I'm going to take this equation, Faraday's law, epsilon equals negative N times delta psi over delta phi over delta T. And we're going to leave off the negative sign because we don't care about direction. I'm going to expand delta phi over delta T to be N times B times A times cosine theta over T. And yeah, okay, sorry, I left off the derivative. dt, and this can be a d out front here. Let me just redraw that. Can't be leaving off my derivatives. So rewriting this not to include the negative sign, N d b a cosine theta over dt. When you do this in college, you can have, again, a changing b with respect to time, delta a over delta t, or you could have delta cosine theta over delta t. In this case, I'm just going to focus on not necessarily taking derivatives here, but figuring out at the instant, what is the EMF at the instant the coil is oriented at 0 degrees, and what's the induced EMF the instant the coil is oriented at 180 degrees. I'll take the absolute value of those EMFs and I'll add them up to get the magnitude of the induced EMF. So because I'm looking at something instantaneously, I can drop the change in values and just focus on getting the magnitude of the induced EMF as it rotates 180. So we'll have a maximum value of the induced EMF with n number of coils times the strength of the B field times the area times cosine of 0 degrees plus the absolute value of n times B, all this is over t, plus n times B times A times cosine of 180 all over t, and I take the absolute value of that. I add these up, and this will give me the magnitude. You'll add them, you'll multiply all these terms, NBA over t times cosine of 0, do the same thing, NBA over t times cosine of 180, absolute value, sum, and then you should get the right answer. Okay, practice 5. The diagram shows a bar magnet near an aluminum, or as the British spell it, an aluminium ring. The ring is supported so that it is free to move. The ring is initially at rest. In experiment 1, the magnet is moved towards the ring. In experiment 2, the magnet is moved away from the ring. For each experiment, what is the direction of the motion of the ring? Now remember, the bar magnet is coming in to the ring at experiment 1. So the aluminum ring is going to move such that it wants to get away from that magnetic field because it does things to oppose the flux, to oppose the changing flux. Then when the magnet is extracted from the ring, the magnetic field is changing, it's moving away, the B field strength is decreasing, so guess what the aluminum ring does? It moves such that it wants to enhance that field strength. It's trying to counteract the fact that suddenly this magnetic field is diminishing, so it will move towards the magnetic field. So the magnetic field causes the aluminum ring to move in a way that resists any change in the magnetic field. Hopefully that makes sense. Question number 6. A rectangular flat coil moves at constant speed through a uniform magnetic field. Which graph shows the variation with time of the induced EMF of the coil as it moves from P to Q? So at position P, I can see that the coil is just starting to enter the magnetic field. As such, an EMF will be induced into the coil to oppose the magnetic field. Right here in the middle, yeah, we do have a coil and it's moving through this uniform magnetic field, but the flux density isn't changing. I'm sorry, the magnetic flux isn't changing. Because of that, there should be no induced EMF in the middle. And then as the coil is leaving position Q over here, the magnetic field flux is decreasing, and the coil is going to an EMF is going to be induced in a coil to try to strengthen or increase the magnetic flux. So here an EMF is induced one direction, and then here an EMF is induced in the opposite direction. In the middle, no induced EMF. So based on my explanation, can you determine which of the following choices is correct? Number 7, the current I flowing through loop A in a clockwise direction is increasing to induce current in loops B and C. All 3 loops lie in the same plane. What is the direction of the induced current in loops B and C? We'll use our right-hand rule first to analyze the direction of the magnetic field surrounding loop A, and I'll do this large right here. Loop A, we have current going in a clockwise direction, so your right thumb points in the direction of the current, your fingertips curl around the direction of the wire, and if you've done this correctly, you will see that inside of the coil there is a magnetic field going into the board for loop A. So for loop A, the magnetic field is oriented like this. Now because the magnetic field strength is increasing, it is going to induce EMF in coil B that opposes this magnetic field. Remember the way these field lines are drawn, if I have X and X a magnetic field going into the page, and then another magnetic field alongside it produced by B also going into the page, those two fields will oppose each other. It's like having two south poles next to each other. So B needs to have a field that induces this orientation all outside of the coil. I have A, and then I have B on the inside, which I'm going to change the color. So if A, all inside of A, we have this type of field, then around the perimeter of coil B, I want to make sure that I have the exact same direction for the magnetic field. There needs to be X's on the outside of B, which would mean dots would be on the inside of B. So to get X's on the outside of coil B, I first can just wrap my fingers around the B coil. So my fingers need to go into the board above the coil. That means my thumb at the top is pointing to the left. That means that for loop B, I am inducing a current anti-clockwise or counterclockwise. So I can eliminate choices A and B right now. Now for loop C, same thing. I'm going to go back to loop A, and if there are X's, if the magnetic field goes into the board inside, then the magnetic field comes back out of the board on the outside. Loop C, because the loop A's current is increasing, loop C is going to try to oppose this changing magnetic flux. Loop C is inundated on the outside or along the edge with this magnetic field that is pointing out of the page, which means that the field direction induced by C or induced within C needs to be also out of the page. So we're going to have dots. So same thing, I take my fingers on my right hand and I curl them around C such that they come out of the board at me. And when I do that for loop C, if I want dots here, I know that my thumb has to be pointing up then. And my fingertips curl out on this side. So that means that the EMF induced for loop C is clockwise. So choice C is the right answer. Okay, practice number 8, last question. Please note we did not cover the last two equations in topic 11.1. You should be able to use these equations if you're given an open-ended question on the upcoming exam for topic 10 and 11. I'm just covering things that we really haven't focused on, which is Lenz's law and magnetic flux. So question 8. Two identical circular coils are placed one below the other so that their planes are both horizontal. The top coil is connected to a cell and a switch. The switch is closed and then opened. What is the force between the coils when the switch is closing and when the switch is opening? So remember, just like before, if current is suddenly increasing, you are going to have repulsion, and then if current is suddenly decreasing, you will have attraction. Thanks for watching, and I hope you found this video helpful.